The second talk this morning is by Greg Papliotis, who's from the Imperial College Mathematics Department. We're going to talk about stochastic multiscale systems and coarse-grained. Thanks.
Thank you very much. So many thanks for the invitation, and I'm sorry I cannot really attend the workshop, so I'm here only for the day. So there are three things that I was planning of talking about. So one is how to actually derive low-dimensional coarse-grained models for dynamical systems where there is also noise. Second, so these coarse-grained models involve parameters that one has to either estimate or calculate. So I wanted to give an example of how one would go about calculating these effective parameters or homogenized parameters. And third, I wanted to give some examples of how one could derive low-dimensional models using data. So in the end, it turned out that there was not enough time to discuss about the second part, so how to actually calculate effective coefficients. So I will discuss about this as we go along, but I haven't, there are no slides about the second part. So my plan then is to give an example where one can derive coarse-grained models using analysis, so using singular perturbation theory and techniques like this, and then to give some examples on how one would, what kind of techniques one can use in order to derive homogenized models using data. Okay. So, right. So basically, so this talk consists of two parts that are somewhat separate, but this is intentional. So one example where one can derive coarse-grained models using analysis is dynamical density functional theory. And then the second part of the talk will consist, will be related to data-driven approaches. And what I will present today is funded by the PSRC through these grants. Now, for whatever reason, I decided to write a book on stochastic process. So this was published last year, and if you want just a copy, ask me. I can send you a PDF of the book. Right. Okay. So now the first part of the talk is on time-dependent density functional theory, and this is joint work with Ben Goddard, who is now in Edinburgh. So he was a postdoc at Imperial, and Sarafim Kaliadasis, who is from the chemical engineering department at Imperial. In this part of the talk, then, I will discuss about the system of interacting Brownian particles. And the goal is to derive a closed equation for the one-body distribution function, if you like. So I have a system that of particles that interact with one another, but they also interact with their environment. And I want to obtain a closed description for the statistics of the system that is as simplified as possible. Now, in the calculation that I will present, I want to take into account the inertia of the particles, and I also want to take into account hydrodynamic interactions. And the way that I will model hydrodynamic interactions is through a space-dependent friction tensor. Okay, so then, as I said, so the goal is to obtain a closed equation for the for a reduced distribution function, in particular for the one-body distribution function. And the part of this work that I will not present here is that one can then compare this coarse-grained dynamics to full Landau dynamic simulations, and in fact, it turns out that there's quite good agreement. Okay, so just some additional information and some relevant timescales. So the model that I will consider in the first part of the talk then is n identical particles. And so there are colloidal particles and they are suspended in fluid. So for the model that I will consider, I will assume that I have, if you like, a small system consisting of the colloidal particles that are interacting with another that is coupled to a large system, which is my heat bath, if you like, or in this case is a fluid. Okay, so if you like, this sort of model goes back at least to Einstein's original model for Brownian motion. Now I have, so the particles in the fluid are much lighter, and then they are bombarding my heavy colloidal particles. So in principle, I can integrate out the degrees of freedom that describe the environment and obtain a closed equation for the identical particles, which I then want to coarse grain and obtain some sort of a kinetic equation. So here are some time scales and length scales. So here are the sort of length scale that you can associate with the colloidal particles, and the characteristic diffusive scale of the system, if you like, is written here. So it's 10 to minus 15 seconds. So one of the things that I want to do is to also remove the inertia from the system. So consider the overdamp limit, if you like, in a systematic way that takes into account the fact that the diffusive timescale of the system is actually very short. So my model, and as I said, so this is not a microscopic model. This is a mesoscopic model. I have already modeled the effects of the bath, if you like, of the thermal bath in the system through a noise term here. So it's not the full Hamiltonian dynamics describing my colloidal particles plus the environment. It is written here. So I have the system of so-called Langevin equations. So up to here is Newton's equations of motion, and then I have two additional terms that account for the interaction between the colloidal particles and the fluid. This is linear dissipation, so linear in the momentum, and this is linear noise term. Okay. So I'm using this notation to denote the particle position and the particle momentum. And so I will describe the noise in a second, but let me just say here that I have a space-dependent friction tensor gamma, and I'm using the space-dependent here to account for the hydrodynamic interactions in the system. Of course, the specific form of the friction tensor is a separate issue, if you like, on how I actually model it correctly. But for the calculation that I want to present, so it's just sufficient to assume that it is a symmetric function of R plus some additional assumptions like positive definite and so on. Okay. Now, one natural question is whether I can derive this sort of model from first principles, and the answer is not entirely clear, at least to me. So if I start with the model of particles, so I have my colloidal particles here, and they interact with the fluid, so with all the small particles in the fluid. I could, in principle, write down a Hamiltonian system for Hamiltonian describing the full system. So a Hamiltonian that, so let me write it like this. So I denote by capital Q and capital P the positions of the colloidal particles, by little q and little p the positions of the fluid particles. And I can write this as a sort of a part that describes the colloidal particles. So this would correspond to the equations up to here. Then I have a part that describes my fluid, or I will call it heat bath here. Plus, I have a term that describes the interaction between the colloidal particles and the fluid particles. And if I assume that the dynamics of, that my fluid is initially at equilibrium, then I might be able to integrate out all the degrees of freedom that describe my bath, and then obtain a closed equation for the position and the momentum of the colloidal particles that looks like this. But as far as I know, this has not been done. If I assume a much simpler problem where I have, say, one distinguished particle that is coupled to a linear thermal bath, so I have linear coupling and a linear heat bath. This can indeed be done, so I can integrate out the degrees of freedom that describe the environment, and I can obtain a closed equation for the distinguished particle or Brownian particle or whatever you want to call this, that is of a form similar to this, but it's not quite the same, so it also has memory. It's the so-called generalized Langevin equation. If one wants to follow a similar procedure or carry out this program for a more complicated system of particles interacting with the environment and so on. I mean, there are, of course, a lot of partial results. But if you ask me, okay, so how do you know that this equation is indeed correct and describes the dynamics at the right lengths and time scales, I would answer that this is mostly phenomenological, okay? So, in particular, why should the friction be linear? Why should the noise be white? I mean, there are all sorts of questions that one can ask. But assuming that this model is correct, and in particular, that I have obtained not only this linear dissipation and linear noise, but in addition to this functional form for the friction tensor here, and correspondingly for the amplitude of the noise, then I can use this as my starting point in order to derive a simpler model. Okay, so this is just to repeat what I just said. So this is a mesoscopic model. I'm already at I'm not at any kind of molecular or atomistic scale. And as I said, so in principle, one could derive this kind of Lanzmann equation from first principles. But for this type of model that I consider here, as far as I know, this has not been done in a rigorous and systematic way. And yeah, so and also another issue is whether the fluid is stationary or not. So it's might complicate things. Right, so now if I have my Lanzmann dynamics, then I can associate to it a kinetic equation for the n-body distribution function. So I use this notation Fn of r, p, and t to denote the n-body distribution function. This is telling me what is the probability of my colloidal system finding itself at configuration r with positions p at time t. And it satisfies the so-called Fokker-Planck equation. You can think of this as a kinetic equation, of course, since it governs the evolution of a distribution function, but it's linear. Okay, so the standard nonlinearity that we're familiar with from kinetic theory, say in the Boltzmann equation, is quadratic. Here you can think of this as some sort of linearized version of this, and the collision operator is replaced by this so-called Einstein-Uhlenbeck operator. So up to here, I have the Liouville equation from classical statistical mechanics, and then I add this term that is local in the positions to that describes the dissipation in the system. Okay, now being able to solve this equation numerically is actually would be quite a difficult task, and there are all sorts of problems. I mean, of course, the number of degrees of freedom that we have, but also the complicated structure of this of the friction tensor here. So, if I have a high-dimensional stochastic system, the natural approach to use is to actually go back to the equations of motion, the stochastic differential equations of motion, and then solve them and compute statistics in terms of averages of solutions to the stochastic differential equation. So I go back to my dynamics here. I solve this equation for many different realizations of the noise and a lot of different choices for an ensemble of initial conditions. And then I can compute the expectation value of an observable, say, by calculating the average over all different runs of the dynamics. But for this I have, I mean, this is still computationally expensive because I have to compute the square root here. So I have, I'm assuming that the so-called fluctuation dissipation theorem holds. So the autocorrelation function of the noise is given by the friction tensor, or in other words, the matrix A that multiplies the noise here is basically the square root of the friction tensor. And I will need to calculate this quantity at its point in space, which is also quite expensive. And in fact, one can get an estimate on the number of operations that we need to perform as a function of the number of colloidal particles and so on. So still, it is actually a quite expensive calculation to do. Okay, so the goal then is to try and so starting from this kinetic equation, from the Fokker-Planck equation for the n-body distribution function, to obtain a closed description for a single particle distribution function, and then use this in order to make predictions for the dynamics.
Harry, why isn't your gradient of V of R expensive too? If you have, are you assuming only local interactions?
I will assume that the interactions here can also expand them in like two-body interactions and so on. But this is also a very expensive term to compute. So yeah, so however you wish to count the number of operations that you would have to perform in order to solve this equation, it is very expensive.
Sorry, I'm not so much of an expert, so can you just say a word why here you have multiplicative noise, right? So why did you choose to interpret this in the Ito framework, getting this Fokker-Planck equation, and not in the Stratanovich interpretation, getting a slightly different?
Okay, that's a good question. So for this problem, Ito and Stratanovich coincide, and the reason for this is the following. So here I have a second order. Well, actually, let me just do the calculation. I'll do it in one dimension for one particle because it doesn't really matter. So if I consider, and let's write it as a sort of properly as a system of stochastic differential equations. I have this system. So dqt equals pt dt, and then dpt equals minus grad q v qt dt. I mean, whether this is time dependent or not, again, it doesn't make a difference. Minus gamma of qt dt plus square root of 2 gamma of qt beta inverse dwt. And now your point is that, so why did I choose to interpret this in the Ito sense and not in the Stratanovich sense? So for this problem, actually, the two interpretations are the same for the following reason. First, you can actually see it by hand. So if you write down the corresponding generator and Fokker-Planck operator, you can see that Ito and Stratanovich are the same. But there is actually a more kind of mathematical reason for this. So the multiplicative noise here depends only on the position and not on the momentum. Right. The position is a differentiable function because I gain one derivative here.
Okay.
And then there is a theorem that says that, if the integrand is more than Helder continues with exponent a half, then Ito and Stratanovich are the same. Okay. Any other questions? Okay. Right. Okay. So so I want to simplify things, and I want to simplify them in two ways. So the first one is, as I said, I want to go from the n-body distribution function to the one-body distribution function. And the second one is that I want to pass to the overdamped limit. So I want to neglect inertia. I mean, I want to, in a systematic way, show that in the limit of high friction, I can actually obtain a simpler equation. And in fact, so if so perhaps I should also write this down here. So for my model, so I want to go from the n-body distribution function to the one-body distribution function. And second, I want to pass to the overdamped limit. Okay. Now, if so these are two different, if you like, limiting procedures, and in fact, I also have to think about the order with which I take these limits. But one of the features in the model that I will consider that will complicate things is the fact that I take hydrodynamic interactions into account. If this friction tensor is constant, then passing to the overdamped limit is something that is actually well understood. And so I cite here a paper by Titular from the 80s. I mean, it's something, now it's a standard problem in homogenization theory, signal perturbation theory. If I have space-dependent, so if I have hydrodynamic interactions, then I have to be a bit more careful. And then also combining the two limits, and in particular going from description for the full dynamics to a description for just the one-body distribution function, it's a bit more complicated. So I will do the second part using this mean field approach. So I will try to write down the n-body distribution function in terms of products of one-body distribution functions, and then we'll see how we can combine these two things. Okay, so now at equilibrium, so if I were to study this problem either in the quantum mechanical setting or the classical mechanical setting and in equilibrium, this is related to the standard, if you like, density functional theory of Hohenberg and Kohn. That just checked, so the original paper where they developed density functional theory has been cited 32,000 times. I guess this is a good number of citations for a paper. So let's review their result in the context that I considered here. So, or if you like, this is kind of a guiding, so this result is sort of guides the kind of results that we want to obtain. So if I integrate out then all degrees of freedom from my distribution function apart from one, then I can obtain the one-body distribution function from which I can then calculate the density, if you like, the particle density. Then this result here says that that my system at a fixed time is can be completely described by in terms of this quantity here, in terms of the one-body distribution function. Again, I mean, this is not quite how the result is explained here, and to begin with, this is for quantum mechanics. But this is the sort of thing that I would like to obtain. So to describe the dynamics in terms of a reduced distribution function, or if you like, in terms of the particle density. Now, I want to do things in a classical mechanical framework and also in a time-dependent framework. And this is something that has been studied quite extensively. And in fact, there are all sorts of different time-dependent density functional theories, as they called. And I will show how to derive one of them, if you like. So the final goal, if you like, will be to derive an equation for the one-particle density. So this is the density of the system that has this kind of gradient structure. So it's some sort of a Smoltowski equation, where on the right-hand side I have this vector field A that depends on position, time, and also is a functional, so that I'm using this notation, is a function of the density that I would expect, for example, there is a non-local function of the density. Okay. Now, the kind of calculation that I will present in my overall approach is actually quite similar to the way one goes from the Boltzmann equation to, say, compressible Navier-Stokes or compressible Euler. In fact, in the end, so one derives a system of hydrodynamic type equations with an additional term that accounts for the hydrodynamic interactions. Okay, and one more. So there are all sorts of technical things that I don't want to get into, but one interesting observation, if you like, or rather one interesting question, is whether the evolution equation that we obtained for the one-particle density, or the one, so I have also integrated out the momentum in this equation, so I have just the one-particle density, whether it should be a deterministic or a stochastic equation. So in particular, since my starting point is actually a system of stochastic differential equations here, so it's not entirely clear whether the final equation that I will obtain for the one-body distribution function, whether it should be deterministic or stochastic. So in the equation that I will present, I'm actually averaging over the noise. So I will, in the end, derive a deterministic equation. But this is something that one can discuss, whether the limiting equation, so, or the final result of the analysis should be deterministic or stochastic. Okay, so I don't know how visible this is. But here's kind of the scheme that we will follow. And here are all sorts of different dynamical density functional theories that have been obtained. So what I will do, is this visible? Can you say this? No. Okay, let me just describe it then very briefly. So my starting point will be the n-body Kramer's equation. So the n-body Fokker-Planck equation that describes the full dynamics of the colloidal particles. And then I can do two things. I can first actually go from the n-body distribution function to the one-body distribution function, and then study the overdamped limit. So in the end, this is what I will do, and I will obtain an equation of this form here. Or I could start with the n-body, the Fokker-Planck equation for the n-body distribution function. First pass to the overdamped limit, and then obtain an equation for the particle density. So these two limiting approaches are actually not they do not commute, and in the end, one obtains equations that are actually so the limiting dynamical density functional theory that one obtains depends on the order with which we take this limit. Okay, but so there is a whole zoo, if you like, of the kind of equations that one obtains in the end. Okay, so this. So I'm just rewriting this here. So our approach will be: so we start with the Fokker-Planck equation for the n-body distribution function. We obtain an equation for the one-body distribution function, and then we pass to the overdamped limit. Or we can do things the other way around. There is no commutativity between these two limits, and since there was this Ito versus Sartonovitz issue was already mentioned, there is something similar when passing actually to the limit in the case where you have inertia and colored noise. So the order with which you pass to the limit as the inertia goes to 0 and the correlation time of the noise goes to 0 affects the limiting dynamics. You might get either Ito or Sartonovitz or neither, depending on the order with which you take this limit. Right. Okay. So let's start then. So let me rewrite then the equation, the Langevin dynamics in this form. So here's the dissipation. Here's my friction tensor. This is the force field, and this is the noise. And now I want to rescale things. So I have already introduced a parameter gamma that denotes small gamma, that denotes the friction coefficient of a single particle. And I want to pass to the limit where this friction coefficient is large, after I obtain a closed equation for the one-body distribution function. So if I then introduce a non-dimensional parameter that scales like 1 over gamma, then my Fokker-Planck equation looks like this. Okay, so I have done my rescaling, and I can now pass to the overdamped limit. And now I think, so those of you who are familiar with homogenization theory for stochastic differential equations, I think at least the scaling starts looking quite familiar. So I have terms that are of order 1 over epsilon, and then I have terms that are of order 1 over epsilon squared. So there seems to be some hope of actually eliminating, being able to pass to the limit as epsilon tends to 0, and then I will have to use standard sort of singular perturbation theory, use Fredholm's alternative, and things like this. Okay, so before I, so this is one thing. I can rewrite my Fokker-Planck equation in a form that looks like this. So this is for the this is the n-body in fact, no, there's no term like this. So it's written in this form, so I can start expanding in powers of epsilon. But as I said, I need to consider another simplification, if you like, or reduction in terms of the complexity of the system.
You're going to let epsilon go to 0.
Yes. I will let epsilon go to 0, but before this, I will actually obtain an equation for the one-body distribution function. There are two things I want to do.
Can you define those fractions as epsilon go to 0?
So let me, let's go back here. So I consider the overdamped limit. So I have a parameter describing the friction coefficient of a single particle. I'm assuming that is large, which means that I can introduce the small parameter epsilon. That has, it's non-dimensional, so that's why I have it has to be defined in this way. So the Fokker-Planck equation for the n-body distribution function has this form. Okay. Now, there are two things that I want to do. So I want to pass to the limit as epsilon tends to 0, which would correspond to the overdamped limit. And this would mean that I will be able to obtain an equation in configuration space, if you like. So momenta thermalize very quickly, so I can average over them and then obtain a closed equation in configuration space. So this would offer some simplification in the sense that I would go from an equation in phase space to an equation that involves only positions. But I want to do another thing. So I want to also, from this equation, obtain a closed equation for the one-body distribution function.
Sorry, just a little thing. You dropped the time dependence in the potential. In the adiabatic approximation, is it important or not?
Okay, so in this, so from now on at least, I will consider the case where the potential does not depend explicitly on time. So for the calculation that I want to do, I don't think that this would play much of a role. But at least this calculation that I will present.
Even if V is periodic, for instance, like rocks from the outside?
So you mean if V is a periodic function of time?
Yes.
In this case, you would also have to do an addition, perhaps averaging with respect to time, but I do not consider this problem. Okay. So I will consider the case where, from now on, where the potential is a function only of space and not of time, and I will present the assumptions that I will make on the potential. Any other questions? Okay, so then let's see how the equation for the one-body distribution function will be. So I define reduced distribution functions in terms of this formula. I'm integrating out n degrees of freedom, and then I also want to, so I have some sort of a normalization constant in front. If I go back to my rescaled Fokker-Planck equation, now I can integrate with respect to n-1 particles here. And then this term here, of course, presents no problem. I'm just integrating. With this term here, I have to be a bit careful because I have this momentum here, so I have to see how exactly to integrate. Similarly here, so let's see what happens if I actually do this calculation. So for here, so this part here, it's actually just the, if you like, the advection operator. And then there is this term that involves the potential that, again, so here, I mean, I haven't been able to just integrate out all degrees of freedom explicitly, so I still have to do something with this term. And then there is this collision operator type term that I have written in this form here. Okay, so again, it's a calculation that one has to do. So you just integrate with respect to n-1 particles here, and some terms can be immediately closed, some terms cannot. This is what we end up with. Okay. So here's my assumptions on the potential, and here I have introduced back the time dependence, but let's not worry about this, okay? So, I mean, the time dependence here is in the one-body, in the self-interaction term, if you like. But let's ignore this. Let's not worry about the time dependence here. What I'm assuming here on the potential is that I have, if you like, a confining term here, or anyway, a term that depends only on the particle position, and then I have two-body interactions. Okay, and I stop here. I can do an expansion of sort of general potential where I include also like three-body interactions, four-body interactions, and so on. But this will complicate the calculation quite considerably. So I stop here, but with the understanding that I can extend things. And I do I make a similar assumption for the friction tensor. So I'm assuming that it consists of I decompose it into a part that is constant plus additional terms, and I have again two-body interactions. Okay, so they're pairwise terms. And one interesting remark here is that I'm not necessarily assuming that I have no off-diagonal elements. So there are diagonal elements. I have diagonal elements here, and I also have off-diagonal elements here. And the two bad interactions that are included in the diagonal terms are described in terms of this function Z1. The off-diagonal terms are described in terms of this function Z2. In the limiting equation that I will obtain for the particle density, if I were to remove this term, I would get a quite considerable simplification. But for the analysis, it doesn't really matter. Okay, so these are my assumptions, that I have two bad interactions, plus that I make the so-called Enskog assumption here. So I write the two-body distribution function as the product of one-body distribution functions times this function here that, that I will assume that I know. I mean, if I were to include also here dependence on momentum and on position, of course, this would be just an identity, because I could include all dependence on all correlations between the particles in this function. So the assumption that I'm making here is that there is no explicit dependence on momentum and on time.
Right. This is very specific structure for the matrix gamma. My question was when you mentioned at the beginning that you need n cubed operations at each time step. Have you tried to explore? I mean, I know this is not the main topic of what you're saying, but just that n cubed seems to be quite large.
Yeah. Okay.
Unless you do something like you could do some smarter things with these matrices.
Absolutely, you're perfectly right. So you can certainly do something smarter with these matrices because there is a lot of structure. Now, of course, the next question is, okay, how do you choose these functions Z1 and Z2? And then this is again a separate problem, but these are quite complicated terms, right? And then there are sort of phenomenological potentials also, and also phenomenological terms for the friction tensor. So they are quite complicated functions, but you're perfectly right that in principle I could take advantage of the structure of the friction tensor in order to reduce the complexity of the calculation of the square root. In fact, in the I will not talk about this part of the work, but we have done simulations where we compare the results that you obtain from the dynamical density functional theory that I will present with full Lanzmann dynamic simulations, and the agreement is quite good. And when doing the full Lanzmann dynamics simulations, there actually we had to be quite careful with how we calculate the square root and so on.
Because you might also decide not to calculate that square root, but just to calculate the effect of that square root on the white noise, which is what you want at the end. So you never calculate the matrix; you calculate directly the vector.
Yeah, that's another good remark, and perhaps we should talk further about this. Yeah. So, but of course, you're perfectly right. So somehow, comparing a suboptimal method with a detailed analytical calculation is not necessarily the first thing to do. Right? So you have to, discuss this. Okay. So first, in terms of the first two assumptions that I make, so basically this means that we only need to consider the two-body distribution function. I can remove this, but this assumption, I repeat what I said. So I can have three-body, four-body distribution functions, but then the calculation becomes much more complicated. Okay, but it can be done. Now, the choice for this, I think, is called pair correlation function. So if I were to set it equal to 1, then this would correspond to the mean field approximation. I'm just assuming that, it's not necessarily 1, but it is a known function. Okay. In fact, in principle, I should also assume that it depends on the friction coefficient, but I'm not. I will not do this because it will complicate the analysis. Right. Okay. So then, if I do this, and then I can actually pass to I can obtain a closed equation for the one-body distribution function. So this is basically this equation here, rewritten after I have integrated out n-1 particles. I have this advection term here, which has the same kind of functional form that I would expect. Okay. I have this term here now is the Fokker-Planck operator, or the Onstad-Lundbeck, the Fokker-Planck operator for the Onstad-Lundbeck process for one particle. Okay. And now I have this quadratic nonlinearity here that involves all sorts of terms. Okay. Now, this looks quite complicated, but at least in terms of the structure of the equation, I'm in sort of well-known territory, right? So I have a kinetic equation for a reduced distribution function. So it's not surprising at all that I have a quadratic nonlinearity. Again, think of the Boltzmann equation. And in fact, there are lots and lots of techniques that have been developed in order to analyze the Boltzmann equation with this particular scaling. So I can use this kind of techniques in order to actually now pass to the overdamped limit. Okay, so let me repeat. So what I have done first is to rescale my equation by taking into account that I have a small parameter associated to the large friction coefficient of a single particle. And before passing to the overdamped limit, I have actually integrated out n-1 particles from my equation under the assumption that I have pairwise interactions and that I know the pair correlation function. Okay, so I know this function here. Okay, and there are all sorts of functions that describe the hydrodynamic interactions and the two-body interactions here that someone has to give them to me, either by doing full molecular dynamic simulations or in any other way. So now, once I have obtained this nonlinear equation, I can use singular perturbation theory in order to pass to the limit as epsilon tends to 0. In the standard form of homogenization theory, if you like, I actually have linear equations. But this nonlinearity actually does not really complicate things too much, because when I expand in powers of epsilon to linear to leading order, I get a linearized version of this. Yes, please.
Back to the Langevin world, like your N-SCOG approximation, how can you relate it to some independence properties of two particles? Or
okay, now if I this equation that I have obtained here, which is based on my assumption that I have pairwise interactions, I cannot see a direct probabilistic interpretation of this, because the way I have worked so far, if you like, is that I have a stochastic differential equation, and to this I can associate a linear equation for the probability distribution function. Now, this equation here is nonlinear. You might be able to associate with this a more complicated stochastic process, like, there are all these super processes and things like that. But the way this is written here is not immediate to me whether it has a probabilistic interpretation. Okay, so in other words, if I were to try to redo this calculation pathwise, if you like, I don't see how, I don't see.
It's just like if you, to integrate the joint probability, it seems that like if there has to be some kind of independence property between the.
Well, I'm making.
And that's on the joint probability.
I'm making some sort of an independence, of an assumption of independence when I write this here.
Yeah.
So as I said, so if I were to set the pair correlation function to be equal to 1, then it would be just the mean field approximation.
Okay.
Now I allow for some freedom here, but still, I'm assuming that I know this function.
Okay.
Now, when you do this, when we expand this equation in powers of epsilon, and then basically this amounts to linearizing this operator here, then you might be able to associate this linearized equation with some sort of a stochastic process, and this would correspond to jumps. Because, so the generator of Markov process with jumps is non-local, right? It's an integral operator. So you could, in principle, I will present the linearized version of this, but you would have a part corresponding to diffusion and then a part corresponding to jumps. Okay. In fact, in the work that was done on the sort of rigorous analysis of linearized Boltzmann models in the 70s, there was always this connection between the linearized Boltzmann equation and jump processes that was used. Any other questions? Okay. Right. Okay. So I have discussed about most of these things, but now, from now on, it's an exercise in kinetic theory, and in fact, for the students in the audience, there is a great book on kinetic theory by Rizibois and Deliner. classical kinetic theory of fluids. And in 77 where you can find all the necessary material on how to do this calculation. In fact, I think this book is great, and I always tell my students and postdocs that they should read it. And this part of the talk that I will not really present on how to actually calculate homogenized coefficients and so on, using again tools from sort of kinetic theory, is also contained in there in a very hidden form. Right. Okay. So let's then finally present the results. So now I need to make some assumptions on the existence and uniqueness of solutions. Well, actually not uniqueness, on the existence of solutions to this limiting equation, as well as the existence and uniqueness of solutions to the full to the previous equation that I presented, that I won't get into. So there is actually quite a bit of analysis that still remains to be done. But if we assume that everything is that all these equations are well defined and so on, then we obtain a nice Smoluchowski type equation for the density. Okay, so this is the well, 1 distribution function, or the particle density. It satisfies this very nice equation here, which is some sort of a continuity equation, and the vector field A is a solution to this integral differential equation. So it's a complete system, if you like. I mean, it's a closed system for the particle density, but it also involves requires the solution of an integral differential equation that is written here. Okay, so there is I mean, the next question is how do you actually solve this equation numerically? But in terms of the formalism, at least, we obtain a very nice closed equation for the particle density. And in fact, if I assume that there are no off-diagonal elements in the friction tensor, then I get something that starts looking very familiar. Okay, so let's make this assumption. Let's assume that there are no off-diagonal elements in the friction tensor. So now I get something that up to here is actually just the standard, the Fokker-Planck equation for the overdamped dynamics, so this so-called Smoluchowski equation, with, though, a space and time dependent diffusion tensor here. And then there is this additional term that involves, again, 2-point correlations. So I can write it in this form, and then I'm assuming that I know this function here. And the friction tensor is given by the diffusion tensor is given by this very complicated, well, actually, no, it's not very complicated. It's given by this formula here. Okay, so actually, I like the mathematical structure of this problem a lot, and I like it that somehow you can see exactly where the hydrodynamic interactions enter. So they enter into this term here, into the diffusion tensor. Okay, so if you like, you can forget about the previous model that involves off-diagonal elements in the friction tensor, and you can think of this as the result of our this calculation. So I have a nice Fokker-Planck type, non-local, non-linear Fokker-Planck type equation for the particle density, and in order to calculate this, I have to also compute this quantity here. I mean, it's fully coupled, of course, because the diffusion tensor here depends on the density. Okay. Now, as I said, so we don't have any existence and uniqueness theory of solutions for this equation. In principle, since it has a gradient structure, one could try to use all these recently developed tools on using Wasserstein metrics and so on, but we haven't done it. Okay. Right. So now, in terms of the level of simplification, I think we have actually done a reasonably good job in the sense that we started with the full n-body dynamics, and now we have an equation for the just one particle distribution function. So I think it's actually quite good. And these equations can be solved quite efficiently. I won't get into this, but in terms of the computational complexity, there's certainly some gain. Okay, now just a few comments on the proof. And so I don't know how familiar the audience is with standard like homogenization, averaging arguments, and so on, but it's basically exactly the same. So as I have already mentioned, so the one possible difficulty is the fact that you have this quadratic nonlinearity. But the point is that when they do the Hilbert expansion, then you're actually linearizing around the Maxwellian, if you like. So then the structure of the problem is that it's standard, and just like with all this singular perturbation theory type of calculations, what we need to do is to understand the operator that appears here. Okay. In fact, there should have been an F not here. So we're linearizing around the Maxwellian. So you can see that sort of you can prove that this operator is dissipative, has a nice has a one-dimensional kernel, and so on. There is quite a bit of analysis that one can do, and in the end, we can solve this hierarchy of equations and obtain a closed equation. Okay, so I think I have some more results about this, but perhaps I should. I don't know, how much time do I have? 20 minutes. Okay, so right. So perhaps I shouldn't get more into this. So let me just present again the final result that we have here, and I'm happy to discuss about the details of the derivation and of sort of further open questions, if you like, during the lunch break. Okay, are there any questions? Right. Okay. So this is an example of a derivation of a closed equation for a reduced description of the system, if you like, so involving only a selected number of degrees of freedom that is based on analysis and on sort of standard tools from kinetic theory and so on. Now, in the remaining 20 minutes, I want to present a completely different approach that is based on data. So suppose, for example, that I have some measurements. So I have my colloidal particles and so on, and then I have some measurements of position, momentum, I don't know, pressure, and so on. And then I want to fit this data to a stochastic model of this form. Okay, so my approach now is different. So it's not, it's based on, if you like, on postulating that a simplified coarse-grained model exists, and I want to derive the coefficients that could describe the potential here or this term here and so on, using observations, from observations. Of course, I cannot do this for a complicated system. Okay, so okay, let me not discuss more about this. So let me move to. Yeah. Okay. So of course, I cannot carry out this program for a system that is as complicated as the one that I just described, but I can still. I can say something for simpler problems for which I still have a clear separation between the degrees of freedom that I'm interested in and the degrees of freedom that I can ignore. So the setup that I will consider on the last 20 minutes of my talk is the following. So I'm given a time series, either generated by full molecular dynamic simulations, if you like, or from actual measurements. And I want to fit this time series, or this data that I have, to a simple low-dimensional model. There are several technical difficulties in doing this, and in particular, the problem is that the data that I have, which is generated from the full dynamics, or is based on observations of the full system, is actually compatible with the data only at the length and time scales at which the coarse-grained model or homogenized model that I want to write down is actually valid. So this leads to inconsistencies between the data that I have in the model to which I want to fit the data. And in the statistics literature, this is usually called model misspecification. So I want to estimate the correct parameters, but in the wrong model in some sense. Now, there are different areas in which this kind of ideas can be used. So I will present some examples motivated by molecular dynamics, but of course, you can think of similar questions in econometrics and also atmosphere ocean science. Okay, so let's then see how we can carry out this program. So I start with a dynamical system that is described by this system of equations. You could think of this variable ZT describing the full Hamiltonian dynamics, right? I mean, of course, we're not there yet, but this would be the sort of full dynamics that I want to study. And then I make a decomposition into the resolved degrees of freedom and the unresolved degrees of freedom. Again, for this model here, the resolved degrees of freedom would be the ones describing my colloidal particles, and the unresolved degrees of freedom would be the degrees of freedom that describe the environment. Okay. Also making, I mean, it's natural to assume, of course, that the number of resolved degrees of freedom is much, much smaller than the number of the unresolved degrees of freedom. Otherwise, there's not much point or much hope that we will gain anything by integrating out the unresolved degrees of freedom. And the next assumption that I'm making is that, in fact, there exists a stochastic model that describes the resolved degrees of freedom. So again, in this model that we looked at in the first part of the talk, I assume that I have a Langevin equation that describes the dynamics of the colloidal particles. And then I said, okay, in principle, we might be able to derive it from first principles, or at least we might know its functional form from first principles. And then there are lots of parameters that are left there, and which I expect that I might be able to estimate using data. Okay, so this is my reduced model, and you can think of it as being the Langevin equation. And the setup that I will consider is that I am given noisy observations. So the noise here might be the actual observation noise in the case where I'm actually measuring things, and of course there is measurement error. Or if I'm generating data by solving the full dynamics here, okay, and then I try to fit a time series obtained from the full dynamics to the Langevin dynamics that describe only the coordinates of the colloidal particles, then the discretization error can actually be included in here. And I will consider the problem where I'm actually assuming that I know the functional form of my coarse-grained equation. So I don't have to obtain the actual functional form of the drift and the diffusion, but only parameters. You can consider similar problems in a fully non-parametric framework, but this is actually, it's much more difficult than what I will to talk about today. Okay, so this is what I want to talk about then now. And I mean, in some sense, what I want to do is quite standard, right? So that somehow I want to parameterize all small scales or sort of unresolved degrees of freedom in the system. But I want to do it in a way that takes into account the fact that there is a lot of data. So let me consider now a much, much simpler example for which one can see what can go wrong. And I might actually have to stop with this. So rather than considering like n-body interacting particles and so on, I consider a single particle moving in a thermal potential. So I consider a particle moving in a potential that has small-scale fluctuations. Okay, and I know that there exists a coarse-grained model for describing the dynamics of my particle in the limit as the period of oscillations goes to 0, if you like, so in the limit of infinite scale separation. So my coarse-grained model then for this, when I start with this equation here, is a simple model like this that does not have any fluctuations. Okay, the data that I use is a time series obtained by solving accurately the full dynamics, and I want to fit this data to a simple model that has no fluctuations in it. You can think of a potential that looks like this. So I have, say, a bistable potential, and then I superimpose small-scale fluctuations that can be either periodic or random. So I have some sort of an average potential here, And then I want to understand whether the time series that I obtained from the full dynamics can be used in order to estimate the parameters in the reduced model. Okay, so in fact, so since I don't have much time, let me just tell you quickly what happens. So it turns out that if I use the standard techniques from statistics for doing this, so like maximum likelihood or the formula for the quadratic variance for estimating the for the second moment in order to estimate the diffusion coefficient. These kind of techniques are actually biased. So the fact that I have this multiscale structure in the problem means that I cannot really use the standard statistical techniques. Perhaps, okay, let me describe this in some detail, and then I will present some more examples. So if I, let me present some numerical experiments. So first, if I consider the case where I have periodic fluctuations, I know what the homogenized equation is. I know how to calculate these coefficients here. So this is a nice simple model where I can test ideas because I actually know what the homogenized equation is. So if I so I will generate then data from the full dynamics. I will feed it to the homogenized dynamics, and I will check whether the values that I get for the parameter that appears in the drift and the parameter that appears in the diffusion coefficient are actually compatible with the correct values that I can calculate using analysis. And for this estimating procedure, I will use the so-called maximum likelihood. So I can, I mean, I don't have time to explain how one derives the likelihood function, but I can, there a standard technique for doing statistical inference for stochastic systems is by using the likelihood function. So I want to maximize, if you like, the likelihood that the data that I have is compatible with the coarse-grained model that I consider. In fact, okay, so for the diffusion coefficient, I have the quadratic variation. For the maximum likelihood estimator for the coefficients that appear in the drift has this very nice, clean form. And of course, the value that I get that I get for the diffusion coefficient and for the coefficient that appears in the drift appears on the depends on the path. I mean, these two are random variables, and for different realizations of the noise, I will get different values. If I use then these techniques and then these formulas in order to estimate the data, and then I generate data from the full dynamics, and I make sure that the discretization error and so on is quite small, then I want to see whether I can use the data in order to estimate the homogenized coefficients. And in fact, I cannot. So here what I do is I just take a simple quadratic potential. So there is just one parameter in the drift that I need to estimate, and the diffusion coefficient. And this is the correct value for the coefficient in the drift and for the diffusion coefficient that I can that I obtain using homogenization theory. And this is what the data is telling me. So it's actually completely wrong, and it's uniformly wrong in the small parameter. So even if the scale separation increases, the maximum likelihood estimator and the quadratic variation, they actually give completely wrong results. They are not compatible with the data that with the homogenized model. Okay. Now, in standard, so one of the things that we learn in statistics is that if my model was actually compatible with the data, then the maximum likelihood estimator should be asymptotically unbiased, meaning that if I increase the length of observation, the formula that I get from the, so the maximum likelihood estimator should converge to the correct value for the coefficient that appears in the drift, and similarly for the quadratic variation. So the reason why this happens is precisely because of the presence of two characteristic timescales in the problem. And you can quantify this. Let's see now what the solution to this problem is. So I can ignore all data at small scales, since I suspect, if you like, that the problem comes from the fact that the data that I have is not compatible with the model that I use, the homogenized equation, at all scales, but only at large scales. Then let's see whether if we simply ignore data, we might do better. This sounds a bit counterintuitive that we're ignoring data, but the point is that all the data that we have at small scales, first, is very highly correlated, and second, is not really compatible with the model that we want to use. And in fact, that seems to work quite well. So I have now the estimator for the drift, the estimator for the diffusion coefficient, and I plot them as a function of the sampling rate. So if you like, the amount of data that I ignore. And assuming that I choose the right sampling rate, I actually am spot on. So I can estimate parameters in the homogenized model using data, provided that I ignore all small scales. Okay. So one can, in fact, okay, so there are all sorts of examples that one can, I mean, you can check that this is indeed the case by looking at all sorts of different potentials and so on, and using maximum likelihood to estimate parameters. And in fact, one can prove things. So first, in the case where you have no subsampling, you can indeed prove that the maximum likelihood estimator, let's focus on this, is indeed asymptotically biased, and that it converges to the parameters in the unhomogenized model. So in fact, in the limit as the time series of observation, the time length of observation goes to infinity, and the scale separation goes to 0, the maximum likelihood estimator gives you completely wrong results. So you're only, you can only measure the parameters in the full dynamics, which is not what one wants to do. And I mean, this is something that has also been observed in econometrics and so on. So it's not, it's well documented that in the presence of sort of a multi-scale structure in the problem, the standard estimators, they become biased. If I then subsample at the right rate, so delta is my sampling rate that depends on the small parameter that I have in the problem, and if I choose then this if I introduce this new time scale, if you like, related to the sampling rate, that is between the small and the large, which is order 1 scale in the problem, then in fact I can estimate parameters correctly. So I can estimate the coefficients in the drift and the diffusion coefficient. Okay, so if we use subsampling, then we can indeed estimate correctly the parameters in the homogenized model. And one can extend this in this result in all sorts of different ways. So if I have a system of stochastic differential equations with well-separated timescales, then I can prove that the parameters in the homogenized equation in the coarse-grained model can be estimated correctly using full simulations of the simulations of the full dynamics, provided that I subsample at the right scale, at the right sampling rate. So provided that I ignore all data at small frequencies. Now, of course, you will tell me that, well, you know, just ignoring data is not the most clever thing to do, and how can you improve this? Yeah. Okay. And in fact, there are things that you can do in addition to subsampling. So you can, for example, average over the data, or you can combine these kind of ideas with some sort of a bias correction step and so on. So there are lots of things that one can do. Or in fact, one can use a completely different approach that does not involve subsampling, but is more, that does not use the maximum likelihood estimator, but is closer to the so-called method of moments. I don't really have time to discuss about this. So this is, as you can see, I was very optimistic about this stuff that I could talk. But so anyway, so there is some joint work with Sebastian Krumsat, who was a PhD student at Imperial, now he's at EPFL, who developed an alternative technique to estimating parameters in coarse-grained models. And rather than describing the technique, I will actually show you how it works to a real data set. Okay, so let me describe the problem that I want to look at first. Right, okay. So here's a time series of observations of this delta 18O, which is a proxy for temperature over the North Atlantic, over a period that is like from 20,000 years before to 70,000 years before. So this is usually called paleoclimatic data, and it's supposed to be stationary. In fact, the time unit that they're using in this business is kilo years, which I think is quite interesting. Anyway, so okay, so I have this time series here, and I want to fit it to a low-dimensional stochastic model. Now, this fits into the framework that I have been trying to develop, because of course, the system that is described through this time series is not one-dimensional, right? So we have a very complicated, very high-dimensional system. We're interested in one selected degree of freedom, and then we want to use this kind of approach that takes into account the fact that I have the starting point is a very complicated system with many characteristic timescales and so on, in order to fit this data to a simple model. So this was already done in this paper here using this so-called uncentered Kalman filter. There are some technical problems with this, in my opinion, at least. But anyway, so let me just show you what we have. So using this technique that Sebastian and Krumzeit developed, we can right. Okay. So here's what we do. So we assume that we can fit the data into a simple bistable model. So in this time series that I presented, the system basically exists in two different metastable states, one corresponding to a sort of ice age and one corresponding to a warmer period. So it's reasonable to assume that I can model the dynamics by using an equation that looks like this. So I have a simple, the simplest possible model you can think of that exhibits metastability, and I consider potentials that have this shape, and one minimum of the potential corresponds to this colder period in their model, and one minimum of the potential corresponds to the warm period. So hence the models that we make there. And then you can argue, well, it's not clear whether the noise in this model is additive or multiplicative. In any event, so if we use our technique, then we can reproduce the data in actually a quite, I think it's a quite, I mean, by looking at this time series and looking at this time series, you can see that it is actually quite close. But more importantly, we can actually compute, using our reduced model, we can compute how long it takes on average for the system to jump from one state to another. Okay? So we can do this. So first we derive the stochastic model, and then we use mean first passage time type calculations to compute how long it will take for the system to jump from one state to another. And in fact, we can compare this with data that exists in this literature. And the result that we get is actually not bad at all. So I don't know whether it's written here, but anyway, so we have here also the probability distribution function of the mean first passage time and so on, and we can get quite accurate results. So of course, I mean, I didn't have time to explain this new method that we have introduced, but the point that I want to make is that in fact this is not only sort of purely academic. You can actually use it in order to analyze real data. And we have also looked at different data sets also from marine ecology and so on. I mean, so it seems that whenever you have problems for which you have some sort of a metastability, if you like, and so on, so this kind of techniques that we have developed, they seem to apply. So, okay, perhaps I should stop here. Okay, so thank you very much.
Any other questions? Quite a few from the top. Okay, so with that then, thank you again.
Thank you.